Welcome back. Let's look at some example problems involving vectors. Alright, so here's our first example. We want to label the vectors in the graph below by identifying their initial and terminal points. And so in our graph here, we have three different vectors, vector v, vector u, and vector w. Now for each of those vectors, we also have some points, which are going to be the initial and terminal points for those vectors. And what we want to first do is determine how we would label each of them using those points, which you can see have some letters associated with them. And so let me show you what I mean. Let's start with vector v. Vector v could also be represented by using the initial and terminal points. Now notice that we have a point S and we have a point X. How do we know which point is the initial point and which point is the terminal point? Well, the initial point is the point where the vector begins, and the terminal point is where it ends, where the vector is headed. So if we look at vector v here, the vector is directed towards point S, right? That is what this arrow is telling us. So we can conclude that vector v starts at point X and ends at point S. In other words, X is our initial point and S is our terminal point. So what we could say is that vector v is equal to vector x, s. We have the letter for our initial point and then the letter for our terminal point, and we use that vector notation to denote that as a vector. All right, so that's how we can label vector v. Now what we also want to do is actually explicitly write out what the initial point and terminal points are. And so let's do that next. I'm going to put those in two different columns here. We'll put the initial points here and the terminal points here. For vector v, our initial point is x, and x, this point is located at 1, 1. So our initial point is x, and it's located at 1, 1. And then the terminal point is s, and s is located at 3, 4. So I'll write s, and that is the point 3, 4. Okay, so that's it for vector v. We have now identified our initial and terminal points, and we have also labeled that vector using those points. But now let's move on to our other two vectors, and before I work through each of them, I would encourage you to pause the video and try to see if you can fill out this table for each of those vectors yourself. See if you can label each of these vectors using those letters and writing out what the initial points and the terminal points would be. So if you want to do that, feel free to pause the video and try it for yourself. But when you're done, or if you just want to see the answers right away, I'm going to show you how to do it. I'm going to work on vector u next. And so if you look at vector u, the vector is directed towards point A. So the initial point is point C, and the terminal point is point A. So we would say that vector u is equal to vector CA, the initial point and then the terminal point. Okay, now the initial point, point C, is at the origin. So our initial point is C, and it's at the point 0, 0. And then our terminal point is A, which is at the point 2, negative 3. So our terminal point is point A, which is at 2, negative 3. All right, and now finally, let's look at vector W. Vector W can also be represented using its initial and terminal points. We have points Q and H, but note that the vector is directed or pointing towards point H, so the terminal point will be H, and the initial point where it begins will be at point Q. So vector W can also be represented by vector QH. Okay, so our initial point is point Q, and if we look at our graph here, point Q is located at negative 2, positive 2. So I'll write that down. Point Q is at negative 2, positive 2. And then our terminal point is at point H, and H is located at negative 3, negative 2. So I'll write negative 3, negative 2. Okay, and so now we have completed this example. We have labeled each of these vectors using their initial and terminal points, and then we have also explicitly written out what those initial and terminal points are. Okay, let's take a look at a different example. Okay, so next up we want to find the component form of vector v in the graph below, and then sketch the vector with its initial point at the origin. In other words, we're going to be graphing the position vector that we find by putting this vector in component form. And if none of that sounded familiar, be sure to check out my lesson video on this topic first, where I explain what component form is, what a position vector is, and how to find them. But if you are familiar with those terms, let's work on solving this example. And once again, just like with all of the examples in this video, feel free to pause the video first and see if you can solve it, and then see if you get the same answer that I get. But if we want to find the component form of vector v here, what we want to do first is identify our initial and terminal points. And so if you look at our vector here, our vector is directed in this direction towards this point. That's what this arrow tells us. And so our initial point is this point right here, which is at 1, 4. The x-coordinate is 1 and the y-coordinate is 4. So this point is 1, 4. And then our terminal point, where the vector ends, is at 4, 1. So that point has an x-coordinate of 4 and a y-coordinate of 1. All right, so now that we have identified our initial point and our terminal point, and let me write that out explicitly. This is the initial point and this is the terminal point. What we want to do is use those points to find the component form. And so to find the component form of vector v, which we represent using these angled brackets, remember, you do not want to represent a vector using open parentheses because those are used for points, not vectors. All right, so you have to remember to use these angled brackets. But anyway, if we want to find the component form of vector v, what we have to do is take the difference of the x-coordinates for the terminal and initial points, and then take the difference of the y-coordinates for those 2 points. And those will make up the 2 components of vector v as a position vector. So let's start with the x component. What we want to do is take the x-coordinate from the terminal point and subtract the x-coordinate from the initial point. Remember, for each of those differences, you want to start with the coordinate from the terminal point. So the x-coordinate for the terminal point is 4, and the x-coordinate for the initial point is 1. So our x component will be 4 minus 1, the difference of those x-coordinates. Then for the y component of v, we will take the difference of the y-coordinates. So for the terminal point, we have 1, and the initial point, we have 4, so we'll have 1 minus 4. It's always going to be the coordinate for the terminal point minus the coordinate for the initial point. Just remember that the x-coordinates come first, and then the y-coordinates. Okay, but now if we simplify, vector v will be equal to 3, negative 3, because 4 minus 1 is 3, and 1 minus 4 is negative 3. And so that is the component form of vector v. That's how you find it, but that's not everything that we want to do here. We also want to sketch the vector with its initial point at the origin. In other words, we want to graph this new position vector that we found. Vector v is a position vector of the coordinate point 3, negative 3. And so let's graph that. I'm going to draw a small coordinate plane over here in the corner. This will be the y-axis, and this will be the x-axis. And so if this is x equals positive 3, and this is y equals negative 3, then the point 3, negative 3 would be right here. So I'll plot that point. This is the point 3, negative 3. And so if we graph vector v in component form, which is the same thing as just sketching the vector with its initial point at the origin, which is right here, then our vector will look like this. That will be vector v. All right, because remember, a vector that has its initial point at the origin is the definition of a position vector, or a vector in component form. All right, so vector v in component form is the position vector of 3, negative 3, which means it is a vector that starts at the origin and is directed at the point 3, negative 3. All right, so next up we have a very similar example. Once again, we want to find the component form of vector v in the graph below, and then sketch the vector with its initial point at the origin. So we're going to do the same thing that we did in the last example. What we first want to do is identify our initial and terminal points for our given vector. And so here we have vector v, and it is directed towards this point. That's what this arrow tells us. And so that means that the vector starts at this point and heads towards this point. So this right here is our initial point, and then this point is our terminal point. So we'll say that this is the initial point, and this is the terminal point. But now we also want to identify the coordinates for those points. So this point right here, the initial point, is at a coordinate of 2, negative 1. So we'll write 2, negative 1. And then our terminal point is at the coordinate 2, 3. So I'll write that. We have 2, 3. Okay, so now if we want to find the component form of vector v, what we want to do is take the difference of the x and y coordinates between the terminal and initial point. So vector v in component form will be equal to the difference in our x coordinates. So we start with the terminal point and we'll have 2 minus 2. All right, so we subtract the x coordinates, 2 minus 2, and then we'll subtract the y coordinates starting with the terminal point. So we'll have 3 minus negative 1. So we'll write 3 minus negative 1. And then if we simplify, this will be equal to 2 minus 2, which is 0. So we'll have 0, comma 3 minus a negative 1. And if you were subtracting a negative number, you're just adding that number. So 3 minus a negative 1 just becomes 3 plus 1. Those negatives cancel out. And so you'll have 3 plus 1, which is 4. And that will be the component form of our vector v. Vector v is the position vector of the point 0, 4. So if we want to sketch this vector with its initial point at the origin, which is the same as just graphing this position vector, we should first draw the coordinate system. There's the y-axis, and here's my x-axis. And I'll label them real quick. There's the y, and there's the x. This will be y equals 1, y equals 2, y equals 3, and y equals 4. And then we have x equals 1, x equals 2, and so on. Those aren't going to matter so much because if this is the position vector of the point 0, 4, and we graph that point, 0, 4 takes us right here. 0 in the x direction keeps us along the y-axis, and then we have a y-coordinate of 4, so we go 1, 2, 3, 4. So that means our terminal point will be right there for our position vector, and the initial point, of course, will be at the origin. And so now if we draw our vector, it will look like this. It starts at the origin and points towards that terminal point. This right here is vector v, the position vector of 0, 4. Or another way you could view it is that we sketched this vector right here, but moved this initial point to be at the origin, and so the rest of the vector moved with that, and so this is the resulting vector. So here we have a very similar example. We want to find the component form of vector v in the graph below, and then sketch the vector with its initial point at the origin. Same exact directions as the last two examples, but now we have a different vector. So once again, first thing that we should do here is identify our initial and terminal points. You can see that this vector v is pointed towards this point. That's what this arrow tells us. The vector is directed this way, and so this point will be the initial point, and this point is the terminal point. So we have the initial point and the terminal point. All right, now what are the actual coordinates for those points? Well, if we start with the initial point, we are at a coordinate of -4, +4. So I'll write that down, -4, +4. And then for the terminal point, we are at the point 6, +4. So we have 6, +4. All right, so if we want to find the component form for vector v, let's take the difference of the x and y coordinates from the terminal point to the initial point. We'll start with the x coordinates. We will take 6 minus -4. So we'll have 6 minus -4. And then we will subtract the y coordinates. So we have 4 minus 4. They have the same y coordinate, which is kind of nice. So a 4 minus 4. And then if we simplify, this will be equal to 6 minus -4. Those negatives will cancel out, and we'll have 6 plus 4, which is 10. So we'll have 10 comma 4 minus 4, which is 0. And so 10 comma 0 is the component form of vector v. Okay, so vector v is the position vector of the point 10 comma 0. And so let's sketch that vector as well. Here is the y-axis, and here is the x-axis, and I'll label them. So this is the y, and then we have the x. This is x equals 2, x equals 4, x equals 6, x equals 8, x equals 10, and then 12 and 14. If vector v is the position vector of 10 comma 0, and we graph that point, 10, 0 will take us to 10 and then, well, 0. Our y-coordinate is 0, so we stay along the x-axis. So that is where the point 10, 0 is. And so if the initial point for our position vector is the origin, then our vector will look like this. And it will be directed towards that terminal point of 10, comma 0. All right, so that is vector v. Let's take a look at a different example. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. All right, so here's our next example. We want to find the magnitude, or the length, of the following vectors. And we have three different vectors that we're going to work with. Two of them are given to us in component form, right? We have those angle brackets. That's how we know that these are in component form. These two vectors are position vectors of the point that is described by the components of the vector. Now the last vector here is actually given in a different way. We have the initial point and then the terminal point of that vector. So calculating its magnitude will be a little bit different, but it won't be that bad. And I'll show you that when we get there. But let's start by finding the magnitude of our first vector. And if you don't remember the formula to find the magnitude of a vector, it looks like this. The magnitude of a vector v is equal to the square root of the sum of the vector's components squared. So that looks like this. We'll have v sub 1 squared plus v sub 2 squared, where v sub 1 and v sub 2 are the components of vector v. In other words, vector v is equal to v sub 1 comma v sub 2. All right, so to find the magnitude of vector v, we need to take each of the components of the vector, square them, add them together, and take the square root of that value. So if we look at our first vector, the magnitude of vector v will be equal to the square root of 3 squared plus 4 squared. So we'll have 3 squared plus 4 squared. We take the components, square each of them, and add them together underneath that square root. All right, so if we simplify, this will be equal to the square root of 3 squared, which is 9, plus 4 squared, which is 16. So we have 9 plus 16. And 9 plus 16 is 25. So this is equal to the square root of 25, which is a nice number. We know what the square root of 25 is. It's equal to 5. And so 5 is the length, or the magnitude, of vector v. Okay, let's move on to our second vector. This vector, vector u, is also given in component form. So if we want to find the magnitude of vector u will be equal to the square root of the sum of the components squared. So we'll have negative 12 squared plus 5 squared. Okay, and so if we simplify, this will be equal to the square root of 144 plus 25, right? Negative 12 squared will be 144, and 5 squared is 25. And then 144 plus 25 is 169. So this is equal to the square root of 169, which is also another perfect square. The square root of 169 is 13. And so 13 is the magnitude of vector u. Okay, so now we have one more vector to work with here, vector w. This one's a little bit different because it's not given in component form, but we can get it into component form, and that will make finding its magnitude a whole lot easier. So we are given the initial and terminal point here. And by the way, if you're ever given a vector like this, you're told that you have a vector and then it's just a list of 2 points, you can assume that the first point is the initial point where the vector starts, and the second point is the terminal point where the vector ends. All right, so if we want to find the component form for vector w, let's write that out here. Vector w will be equal to the difference between the x-coordinates of our terminal and initial points, and then we'll have the difference of the y-coordinates between those 2 points. Remember that you always start with the terminal point and subtract the coordinates from the initial point. So for the x component of w, we'll have 9 minus 3, so I'll write 9 minus 3, and then for the y component, we'll have 5 minus 10. So we have 5 minus 10. So I'll put this up here. Vector w will be equal to 6, negative 5, right? 9 minus 3 is 6, and 5 minus 10 is negative 5. So now, if we want to find the magnitude of w, the magnitude of vector w will be equal to the square root of the sum of our components squared. So we'll have 6 squared plus negative 5 squared. And 6 squared is 36, and negative 5 squared is 25. So this is equal to the square root of 36 plus 25. And 36 plus 25 is 61. And so I'm just going to erase this and write that that is equal to the square root of 61, which can't be simplified any further. That is in its simplest form. And so the square root of 61 is the final answer for the magnitude of vector w. Okay, and so now we have found the magnitude for each of these three vectors. All right, so here's our next example. We want to show that the vectors whose initial and terminal points are given below are equivalent vectors. Now, what does it mean for two vectors to be equivalent? Well, it means a couple different things. For one, both of the vectors should have the same component form, which then implies that both vectors would have the same magnitude and the same direction. And so there's actually two different ways that we could check to see if these two vectors are equivalent vectors. I'm going to show you both ways here, but you will see that one of them is clearly a whole lot easier and quicker than the other. But regardless, I'm going to show you both for this example. Let's start by showing that these two vectors are equivalent vectors by showing that their length and direction are the same. So what we're going to do is find the magnitude of each of these vectors as well as the slope of the vectors. That's going to be the easiest way for us to determine their direction at this point in Calculus 3. And so let's start by finding their magnitudes. The magnitude of vector u will be equal to the square root of the sum of the components squared. Now you need to be careful here. These vectors are not given to us in component form. We will have to find that. But a quick little shortcut is to remember how we would find those components, right? The x component would just be the difference between the x coordinates of the terminal and initial point. Once again, the first point is the initial point here, and the second point is the terminal point. So the x component for u would be 5 minus 3, and so we'll square that, right? I'm taking this x coordinate and subtracting this x coordinate, so we have 5 minus 3. That would be the x component of u if vector u was in component form. And then we're going to add that to the y component squared. Now the y component will be the difference between our y coordinates. So I have 6 minus 2, and I'll write that in there, 6 minus 2. And if we simplify, this will be equal to the square root of 2 squared plus 4 squared, right? 5 minus 3 is 2, and 6 minus 2 is 4. So we have 2 squared and 4 squared. 2 squared is 4, and 4 squared is 16. So this is equal to the square root of 4 plus 16, which is equal to the square root of 20. Now you could simplify that further. Notice that 20 could be factored to be 4 times 5. And we know that 4 is a perfect square. The square root of 4 is 2. So we could rewrite that to be 2 times the square root of 5. So the magnitude of vector u is 2 times the square root of 5. Let's see if vector v has the same magnitude. The magnitude of vector v will be equal to the square root of the sum of the components squared. But once again, this vector is not in component form, so we will need to calculate those components by finding the difference between the coordinates in our terminal and initial points. So we'll have 3 minus 1 squared plus 8 minus 4 squared, right? The difference of the x coordinates will be 3 minus 1, so we square that, and we add it to the difference of the y coordinates, which is 8 minus 4. Okay, so now if we simplify, this will be equal to the square root of 2 squared plus 4 squared, right? 3 minus 1 is 2, and 8 minus 4 is 4. And this should look pretty familiar. This is the same exact calculation we had for the magnitude of vector u. 2 squared is 4, 4 squared is 16, so we have 4 plus 16, which is 20, which means that this is equal to the square root of 20, and as we said earlier, that is equal to 2 square roots of 5. So both of these vectors have the same magnitude, the same length, so we know that that's the same, but do they have the same direction? Let's check that next. To see if they have the same direction, we will need to look at the slope of these vectors. And so remember that we can calculate slope by taking the difference in the y values divided by the difference in the x values. So for u, the slope will be equal to 6 minus 2 divided by 5 minus 3, right? The difference in the y-coordinates divided by the difference in the x-coordinates. And so that will be equal to 4 divided by 2, right? 6 minus 2 is 4, 5 minus 3 is 2, and that is equal to 2. 4 divided by 2 is 2. And then for v, the slope will be equal to 8 minus 4 divided by 3 minus 1. The difference in the y-coordinates divided by the difference in the x-coordinates. Now 8 minus 4 is 4, and 3 minus 1 is 2, so this is also equal to 4 divided by 2, which is 2. And so the slope of our vectors is also the same, which means that the direction of our vectors is the same. And so since both the magnitude and the direction are the same for these two vectors, we can conclude that they are equivalent vectors. We have now proven that that is true. Okay, so that's one way that you can show that two vectors are equivalent, but there is a much easier way. All we have to do is show that they have the same component form. So let's do that. Let's find the component form of each of our vectors. Vector u will be equal to the difference in the x-coordinates and then the difference in the y-coordinates. Remember to always start with the terminal point, and so we'll have 5 minus 3, 6 minus 2. Right, for the x-coordinates we have 5 and 3, so 5 minus 3, and then for the y-coordinates we have 6 and 2, so 6 minus 2 is what that y component will be. Now if we simplify, 5 minus 3 is 2, and 6 minus 2 is 4, so I'm just going to erase that, and we'll find that the component form is 2, 4. Now for v, vector v, we will have 3 minus 1, 8 minus 4. Right? The difference of the x-coordinates, 3 minus 1, and then the difference of the y-coordinates, 8 minus 4, right here. And so 3 minus 1 is 2, and 8 minus 4 is 4. And so we can erase that, and you will find that we have the exact same component form for vector v as we have for vector u. So if their components are the same, then it would make sense that their slope or direction and their magnitude or length are also the same. So that's why it's going to be easier for you to find them in component form, and if they're the same, then they are equivalent. You don't have to go through this extra work, because if the components are the same, then all the other calculations using those components will also be the same. All right, so if you want to show that two vectors are equivalent, the best way to do so is to just show that they have the same component form. And so let's take a look at another example of that really quick. All right, so here we are once again. We want to show that the vectors whose initial and terminal points are given below are equivalent vectors. And so here we have our two vectors. Same thing as the last problem, except we're not going to do that first method. We're just going to find the component forms of these vectors. And if they're the same, we will conclude that they are equivalent. So let's start with vector u. Vector u will be equal to the difference in the x-coordinates. So we'll have 1 minus negative 4. And then the difference of the y-coordinates, so we'll have 8 minus 0. And now if we simplify, 1 minus a negative 4 is just 1 plus 4, so we have 5, 8, because 8 minus 0 is just 8. Okay, so that's the component form for vector u. Let's look at vector v. Vector v will be equal to the difference in the x-coordinates and then the difference in the y-coordinates. So we'll have 7 minus 2, and then 7 minus negative 1. All right, now 7 minus 2 is 5, so we'll have 5, 7 minus negative 1. That's the same as 7 plus 1, so we'll have 8. And now you can see that vector v and vector u have the same component form of 5, 8, and so they are equivalent vectors. We don't have to show that their magnitudes are the same. We don't have to look at their slope. We can just immediately conclude that since their component forms are the same, these vectors are equivalent vectors. Okay, let's take a look at one more type of problem for this video. All right, so next up we want to find the terminal point given the position vector and the initial point. So this is a little bit of a different problem. We are actually given the component form of our vector. This is our vector in component form. We have those angled brackets. Another way to refer to that is as a position vector, but then we're also given an initial point. And so what we want to do is find what the terminal point would be given this initial point, right? We could pick any initial point we want and find a corresponding terminal point, but we want to find the very specific terminal point for this initial point given this position vector. So let's do that. What we want to do first is just draw a small coordinate system. So I'm going to do that here. This is the y-axis, and then we have the x-axis. And then let's graph our initial point here of 4, 2. If this is x equals 1, x equals 2, x equals 3, and x equals 4, and this is y equals 1, 2, 3, and 4, then our initial point will be right here. That is the point 4, 2. And then in order to find the terminal point, all we have to do is sketch this vector, this position vector, as if this point was the origin. Right, so if we were just going to graph this position vector, we would just plot the point -1, 3, and then connect the origin to that point and draw a little arrow, and we'd have our vector. However, instead of treating the origin as our initial point, we're going to treat this point as our initial point. So what we want to do is move -1 in the x direction and then +3 in the y direction from that initial point. And that will give us the terminal point. All right. So moving 1 in the negative x direction takes us here, and then +3 in the y direction will take us 1, 2, 3 right up here, which would be y equals 5, which I do not have labeled. But let me just plot that point real quick right here, and then I'll just quickly redraw my axis here. This is the y-axis, and this right here is y equals 5. Okay, now that is our terminal point. So now we can draw our vector here and label it. But what we're really interested in here is the actual coordinates of that terminal point, which as we can see is the point 3, 5. So our terminal point is 3, 5. That is the answer to this problem. Okay, and just a quick side note, there is a shortcut to these problems. If you notice, if you add the components of the position vector to the coordinates of the initial point, you will get the terminal point. Right, -1 + 4 gives you 3, and 3 + 2 gives you 5. So that's a quick little shortcut that you can use to check your work, but it is helpful to go ahead and draw it out because it makes you think a little bit more about what a position vector is, how you use it, and what the difference is between an initial and terminal point. All right, but that's it for this video. This was the last example. If you do want to see some more examples, I have more available on my membership site, so feel free to look into becoming a member if that interests you. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I'll see you next time.